Hello? Yeah, Jay, can you hear me?
Yeah, can hear you.
Okay, if I mean the network looks better today, but if there is something, if I drop out or there's a problem, just call me because otherwise I won't be able to hear um, sometimes the messages as well.
Yeah, okay.
Okay, so right, so we'll continue where we left off yesterday. Um, Sorry, just 1 second. Yeah. Um, so yesterday we discussed the concept of impedance and admittance matrix of a network. Uh, the network is basically sort of a black box, even though sometimes you can give it a representation. We looked at a few of those. And then you only define the properties with respect to the terminals. And we discussed under what conditions that is possible. And it's essentially for all practical situations, we'll only be dealing with those kind of networks where at the so-called ports you can define voltages and currents, um, or ingoing and outgoing voltage waves. Uh, we saw the relationship between these two, and then given that you can define the impedance and admittance matrix, which is sort of an extension of Ohm's law, which is V equals to I times Z, to now a more a matrix form with many, many ports in there. And we looked at how to compute that for some simple cases, and we saw why the values are what they are, what is the connection between uh, input impedance and Z11, for example, for a multi-port network. And again, we have discussed many times in the past and also in the beginning of this chapter that actual measurement of voltages and currents is not also possible, even if they can be defined in a unique way. And the more common quantity to be measured is actually the uh, um, are these sorry, I don't know why. Are these incoming and outgoing voltages or current waves. So you can choose either of them. You can choose voltage incoming and outgoing or current incoming. They're essentially going to give you the same information. Typically, it's the voltage which one sort of considers, but even there, it really doesn't matter because almost invariably, what you're interested in are ratios. Okay, so just like the admittance and impedance matrix connected the voltage and current at a particular network to all the other, particular port in a network to all the other voltages and currents in the other ports. The scattering matrix now connects the ingoing and outgoing, incoming and outgoing waves, and that's basically now the definition is you relate all the outgoing waves. So these are all the V1 minuses, and remember the convention I had told you last time is that V minus is the one which is leaving the network. Okay, so all the ones which are leaving the network are what are called reflected waves, or outgoing waves is probably a better um, definition. Um, and so these are all minus, and then all the ones which are coming into the network is plus. So this is, you have to keep this in mind. And then basically just relates each outgoing voltage wave at a particular port to all the other incoming waves at all the other ports, including the port itself. So one will now depend on V1 minus will be S11 into V1 plus, S12 into V2 plus, and so on and so forth. And now you can see the numbering convention which I had mentioned maybe a few lectures back of what it means. Of course, 1 is not very useful to know because you can't figure out what, sorry, not, I don't mean useful to know, I mean that you can't figure out what the two indices mean. But from 1, 2, you can see that S12 is the coefficient which is telling you what happens when V2 plus is incident and what is coming out of V1 minus, right, on the one port. So if this was port 1 and this was port 2, S12 is coming from 2 and into 1. Right? Is that, let me just make sure I'm saying this correctly. So hold on one second. It's a little bit of confusion here.
So you're saying this because you're setting all the other V pluses and V minuses to 0, and you're checking which element relates the V minus to the V plus, right? So
Well,
V1
yeah,
minus.
I haven't come to that part of how does one extract a particular element. I'm just now talking about the convention, because if one just writes down the expression for V1, let's just do this, V1 minus, and let's say just it's just 2 ports, so it is S11 V1 plus S12 V2 plus. So now going further down in this equation 4.41, if V1 plus is set to 0, that means you're not sending any signal in V1 plus, but you're only sending the signal in on, sorry, you're not sending a signal in on port 1, but then this goes away. If you're sending in a signal at port 2, and you see what is coming out of port 1. Yeah, that's right. So that's fine. So V1 minus is equal to S12 V2 plus, which basically what I was telling you is that the first index is the to index and the second index is the from index. Right? This is what looks slightly non-intuitive when you first encounter it. You might say, okay, it's going from the first to the second, but it's actually coming from the second into the first. I mean, the second index. Of course, here the second index is 2 and the first index is 1. Okay, yeah, so this is fine. And so, this is very analogous to how the impedance matrix was defined, but in terms of different quantities. So if you now want to be able to measure this for a particular network, then to isolate one particular term, you have to set all the other ones which are not related to uh, the one you're measuring to 0. So remember that the quantity you are sort of detecting is the minus ones, and the quantity you are injecting are the plus ones. Right? That's where you're sending the signal from. Then you're receiving the signal on this side. So if you have to set all the other excitations to 0 except the one which is specified by the index. So in this case, the 1 of the S12 refers to the receiving port, but the injection port is the 2, that number 2, S12. So only V2 can be active, and since it's only 2 ports, V1 was set to 0. If it was a multi-port, all the other V pluses should be set to 0. Now, what does that mean? In uh, in reality, that we again discussed this last time. What is that correct uh, boundary condition or termination? Is that it has to be a load, okay? And somewhere here it mentions that. Yeah. So except the JS port are set to 0, which means all the ports should be terminated in matched loads to avoid reflections. Okay. So the reflection coefficient of a network is always, and this is very, very important when you're measuring this using a real instrument, which is the network analyzer. There's an image of that. We will discuss this a little bit more later today and in a lot more detail in a later lecture. If you have an N port system with you, all the ports must be connected to either the instrument, which is, say, the network analyzer, or it should be terminated with a 50 ohm load, depending on the quantity you are measuring. Otherwise, it's not going to make sense. This condition that you want all the unwanted V pluses to be 0 can only be ensured if that port is terminated. Okay? Again, might seem confusing or a little obvious, but let's look at this in a little bit more detail. You might say, well, if I'm not sending any signal in, why do I care how it is terminated? And that would be a valid question to ask, except that the V pluses are not really the injected signal, they are the incoming signal. Okay, which means it doesn't matter how they are created. Now, what can happen is if you send a signal in, say, from port 1, some of that could reach port 3. But if you don't terminate this with a 50 ohm load, there is definitely going to be a signal which is going to be reflected and coming back because it won't be matched. And that would then correspond to the V minus, sorry, not V minus, V plus term. See here, the reference points have changed.
Hello. Sorry. Can you please allow Supriya? So I think he's waiting.
Okay, sorry. Yeah, just multiple screens can't see. Let me maybe erase this whole thing here to emphasize this point again. Well, what did I just do? very strange. More and more I'm having problems with this. Anyway, uh, so the point we are making again is in the measurement of a particular scattering matrix element, you need to, so let's say that is Sij, and in this case, you're receiving the signal at port I, and port J is where the excitation is coming from, right? That is the definition of this thing, right? Let's just make sure I'm not constantly mixing this up again. Okay, so Sij V1 over Vj, and Vk plus is 0 for all k not equal to j. So for the ones where j, which is the one you're interested in, is not equal to k, you have to set all of those to 0. And what we are discussing is what does it mean to set them to 0, right? And I said, and the book also said, is that it means you have to connect a 50 ohm load here. And the reason for that is that it's not really the wave you are injecting, it's any wave on that line traveling in this direction, which is the plus direction. And if you don't terminate it with 50 ohms and there's an excitation, say in this port, it's going to travel outwards. And if it is not terminated with 50 ohms, it's going to come back. And then that violates the requirement for that, and then you will not measure this. Okay, so this is extremely important and practical information, is that if you are checking a multi-port device and you are seeing if it is working properly or not, you need to make sure that the ports are terminated appropriately. Now, sometimes you might want to keep it unterminated for some other reason, but by default, you should always make sure that it is connected properly. I just give you an example. This is, we haven't looked at this device in detail, but there is a device called a splitter, which will take input signal and then basically give you 3 dB less power on both of them, so that it's basically half the power approximately. It's called a 3 dB splitter. And if you're measuring this object and saying, okay, let me check whether I get 3 dB loss going this way, it's extremely important that you keep this one terminated with 50 ohms. Otherwise, the other part of the power which will go in, and then it can come back and it will do something weird, like it would then come back into here. All kinds of things are possible. So that is why, and if you're, for example, if you're trying to measure reflection out of this, ideally, all of the power going in should be absorbed. But if you don't terminate that, that power could come back here as well, and you'll measure something incorrect. So it's extremely important to do that as a practical thing as well. And that's basically what the definition of this quantity is also saying. Okay, and these quantities can be measured using a commercial instrument. If you're solving for some network model where the components are given to you, then you can even calculate that. And this chapter has some examples on doing that calculation. For example, for this T-junction attenuator circuit. Okay, so we will look at again the attenuator circuit in terms of the reflection coefficients in just a little bit. There was just a few other points I just wanted to mention here. There are again all the associated properties of the scattering matrix, like we had talked about, reciprocal, symmetric, lossless. What does that do to how the structure of the scattering matrix is? You can go through that. These are good things to keep in mind. In some cases, the mathematics behind this also comes in handy when one is analyzing certain microwave networks, which is part of our research, but we will not go into that in detail. So just go through this, just a useful exercise to know how it comes from. If one is, one of the most important properties is about lossless networks, where no power is lost or generated as in the network, which is, it's an idealized version of what is typically true, because any realistic device will always have losses, but superconducting devices need not. So one comes often very close to this uh, idealized thing about a lossless network, even in reality and not just in theory. So one then sees that such a matrix has to be unitary in order to be a valid thing. And this has sort of connections to other things you know about unitary matrices in other branches of physics. Okay. Then yes, so this is another section you should probably look at. Did I include this in the thing? This is still within 4.4, right? So yeah, so this is again a practical aspect, and I think in the next homework problem, I'll have something related to this. This is practical in the sense in the following way. So you see this object here is the device which allows you to measure the scattering parameters, okay? Which means that anything which is connected at this reference plane and this reference plane, this instrument will give you the correct scattering parameter for that particular device. In this case, let's say it's 2-port or N-port, it doesn't matter. Most real vector network analyzers are 2-port. Sometimes you can have a 4-port as well. I've never seen something bigger than that. Usually such large networks sort of don't really exist in practice, and you can always measure them sort of in parts. You don't have to measure all the ports at the same time. You can even do them 2 at a time if you want, and then recover the whole scattering matrix. So what this is referring to is that sometimes due to practical constraints, you might not be able to connect the devices here at these points. But there is some medium, typically a section of transmission line, which has to be present, and you're only able to put your devices at this reference plane. So then the question is that the instrument is actually measuring the scattering parameters at this plane, but you actually want the scattering parameter at this other plane. How does one go from here to there, right? So in this example, they just talk about a simple case where if this is just a section of a transmission line, an ideal transmission line, 50 ohms matched, then we know again from previous discussions that this sort of does only trivial things, and like for example a phase accumulation. And Joydeep, going back to this very old question you had asked about the phase accumulation, this is basically that. You're going to get an additional phase, but if you're looking at only magnitudes and things like that, you're not going to see any change in the response, but you could see a very different phase response if one doesn't account for that. So when we if the situation is an extremely simple case of an ideal 50 ohm transmission line, which means completely lossless, exactly 50 ohms, which means no reflections, nothing, then it's trivial. It can be just fixed by a calculation, like a change of calculation, which is just of this phase accounting. So you just add a negative phase to that, and that's what this electrical delay setting, which is provided in these instruments, allows you to do that. And one can always try that first to see, okay, does it make sense? So it just sort of resets the additional phase and then plots the thing. But most practical cases, this is not just a simple transmission line. It will have some loss. It might even have some frequency dependence. It could often have not perfect 50 ohms. There could be mismatches at the junctions itself. And these things make things very complicated. Now, having said that, if this intermediating object is really terrible in terms of all of these properties, that is not really 50 ohm, there's too much frequency dependence and all of that stuff. Actually, frequency dependence is still okay because we are mostly talking about linear objects. So, the frequency of all the input and output signals are the same. So you could just treat this object here in the middle as different object for each frequency, and you will have a different calculation or this conversion. Anyway, that is how it is done. It's done for every frequency point independently. but if it has like too many reflections and this whole section also starts behaving like, say, a resonator with standing waves, then you're lost. Like you can't really recover the true scattering matrix of the objects you have maybe connected here by doing something to take into account the middle stuff. So it's mostly for, you know, minor deviations from 50 ohms, small reflections, small losses. Then you can actually recover this, and there is actually a procedure to account for that, and that is called the calibration procedure. So what does that basically mean is you can essentially now think of this this box here in the middle as a two-port network, right? So I'm just talking about two ports here. It says the drawing is one port, but essentially what you now have is you have an object, you have your vector network analyzer. It is connected to an arbitrary S matrix, and this, okay, I should be a little bit more careful here. You should draw two lines for each of these ports because this is not a single port system. It's a two-port on either side, right? And there is some two-port network which is now here. Okay, this is your device which you're trying to measure. Then the question is that if you know the scattering parameters at this reference plane, and you know the S matrix of this unknown object, then you can recover the scattering matrix of the device. Okay. So this is what you would like to do because you want to get rid of the effect of this unknown thing in the middle. And you can do that by a process called calibration. And there are several different techniques. I think this chapter also discusses some of them. And I think in the next problem set, there will be one problem to do that. But the idea is very, it's not simple, but the idea is that if you knew what your device was, of course, in reality you don't, but you can now put in test objects. So these are called calibration standards. So if you now replace your device with, so you know, device is also unknown, because that's what you're trying to measure. Now you replace it with a known calibration. So this is basically a two-port network whose properties you already know because you have made it. Right? This is a standard. You know, practically speaking, you buy these things from the vendor who provides the network analyzer. You get these calibration standards, and because you know what is the network of that, then by seeing that when you connect this known device here, what is measured here, you can invert the problem and basically figure out what is in between. So you see, it's sort of the reverse of the process. You now put a known device to figure out the unknown S matrix in the middle, and then once that is taken care of, then and this procedure is something which the instrument itself allows you to do. So you say that it will tell you connect this standard, and then you take a measurement. Then it will say connect a different standard, and it will take another measurements. And by doing this with sufficient number of these known two-port networks, it will then do a calculation, and then when the calibration is turned on, it's essentially like the reference plane has now moved up to this point. So it will automatically take into account this unknown S matrix, remove it, and show you the actual the calculated S matrix of the device you have connected. Okay, and it's you can sort of see that this would work, and the homework example will allow you to calculate this for a simple case of a single port case. You know, the two port is slightly complicated, but the same problem can happen with a single port, right? So you have this device, and you want to measure the gamma of this guy, but this device and your instrument is has something in between, some S matrix which is unknown. So you're actually measuring gamma prime. Then you want to know, okay, what is really gamma of this device. So you then replace this with some different standards, and typically these are simple things like an open, a short circuit, and a 50 ohm, because these are sort of the simple standard things. And from that, for a single port with these three measurements, you can actually recover this unknown S matrix in the middle. Okay, so I'll give this as part of the next homework assignment. Okay, so maybe let me pause here. If you have any questions so far.
I have one small question here. So in our experiment, maybe let's say we sometimes change our circuit elements. Let's say this unknown S matrix.
Mm-hmm.
So if it changes, then the calibration will have to change every time of the VME.
So if you are changing the device, then no. But if you are changing this intermediate object, which means that you have changed the wiring, then of course the old calibration will no longer work. The system will still output some answer, but it will not be the correct one. So you will have to redo the calibration if you want to get a very precise results. Now, again, in practice, because this unknown object in the middle is typically a simple object, and by simple I mean a cable with a little bit of a loss and maybe some small reflection, it doesn't change the overall properties of what you're measuring dramatically. So it really depends on how accurately you want to measure that you would care about calibration. And also it is more important when you are measuring reflections rather than when measuring transmissions, especially when the intermitting object is not quite problematic. So in that case, you can get away if you know what you're looking for. There is no hard and fast rule for this. It's partly experience, partly understanding what the intermitting object is actually doing. So that's why I said that for the simplest case where it's just a long length of cable, you can just dial the electrical delay and then it's fine. But what it will not give you correctly is the reflection coefficient. And in fact, I'm going to move to microwave office now. I'll explain why that is the case. It's actually fairly straightforward, but it's good to see under what conditions, which quantities are going to give you the information you're looking for, and which are not, is not going to give you the information when you don't know the unknown object. Okay. Anything else? All right. So let me see. There's something else I wanted to mention here for you to look at. Yeah, this idea of power waves is also interesting. Just it's again kind of obvious that the power delivered to a roll will be like mod V plus square minus V naught. So there's incoming power minus outgoing power is the power which is delivered. So they derive that. They also discuss that it doesn't work when you have complex characteristic impedance. Those are not really that much of interest in a practical sense in special cases. Oh yeah, and then there is this other another representation which is quite useful, and it explains here very easily, is that the main advantage of this ABCD matrix over S matrix is that you cannot stack the S matrix. So what I mean by that is that if you have three black boxes whose S matrix let's call them SA, SB, and SC, so the matrices, and if you want to now combine this into one effective S matrix, because it's still just a two-port network with respect to these two ports, then it's not simple to go from here to here. simple in the sense that it's not just matrix multiplication. Whereas if you use the ABCD matrix, which now relates voltage and current on one side to the voltage and current on the other side, uh, then it is possible to do that. Right? So earlier you had the impedance matrix, which had voltage on one side and current on the other side. Then you had the S matrix, which had incoming voltages on one side and outgoing voltages on the other side. And now you have this mixed version, which has voltage and current on one side to voltage and current on the other side. And this one is, you can multiply them. So it's useful when you have to compute the full properties of a composite system, which can be broken down into individual things. And again, all of these matrices are interchangeable. It's just a convenience of which one you use to compute it. Of course, since they're all interchangeable, you can always write down a complicated expression for what is S in terms of SA, SB, and SC. But rather than doing that, what is better is to change S to an ABCD matrix, this to an ABCD matrix, this to an ABCD matrix, do the matrix multiplication, compute the final ABCD matrix, and then invert it to an S matrix. Otherwise, there's going to be like a very complicated, messy formula which is not generic, right? So that's obvious to see. So this is also quite handy, and we use it all the time to go back and forth. I think modern vector network analyzers also have like simple tools inside the instrument where you can change which matrix you're looking for and to just compute it for you, or you can do it later on. And here they have given sort of standard forms of various ABCD matrices of different types of circuit. It also explains here why these two type of networks. In fact, I had mentioned this, I think, in the last lecture, that this P and pi networks are sort of a very generic way of writing down any two-port network. Right? You can always do this, and this allows you to draw simple equivalent circuits for those two-port networks. And of course, those only will make sense if y1, y2, and y3 for a pi network. So again, these two are sort of dual of each other. That here it's in terms of impedances, there it is more naturally in terms of admittances. And then you see there's very nice symmetry between these two cases in terms of that they have the same forms, 1 plus y2 or y3, and this is 1 plus z1 or z3, and so on and so forth. But each of them is, one is admittance, one is impedance. The usefulness comes if y1, y2, y3, or z1, z2, z3 have a simple form, in the sense that it looks like an inductor, it looks like a capacitor, or it looks like a resistor, so that you can then draw the equivalent circuit. I think they sort of discuss one example of a case where you can, this is basically an interface between a coaxial transmission line going on to a microstrip transmission line on a substrate. And this, of course, is very, very common. It's usually not done in the way it's shown here, but we will discuss this in a different class about launching signals, because your instruments and all have coaxial outputs. You have a cable which is bringing the signal, and then you want to go to a circuit board, and on the circuit board you might have a different type of a transmission line, say the microstrip, and then you need some interface which allows you to connect from this signal to that signal, and that has to be, again, a perfect one, ideally speaking, which means no reflections, all the power goes in as much as possible, but there is always going to be some kind of discontinuity, and that can be modeled by these simple P or pi networks. And again, the text explains that you get some intuition from these models that okay, I can understand where this inductance is coming from. I see what this capacitance means. So if you want to fix it or make it better, you know what to do. Okay, so these equivalent circuits are useful in that sense. Again, a lot of these ideas are now not extensively used because everything can be done on a computer, but it's useful to have these intuitions if you're dealing with a practical scenario. So you can read this part, and basically up to 4.4. So the rest of the chapter has some additional details which are not super useful, so that's why I asked you to basically stop here. Okay, so now let's move to microwave office. Yeah. Okay. So this is again the T network we had. I think this was for a 3 dB attenuator. And we, of course, looked at the S matrix as well yesterday. So your this is, of course, magnitude of the transmission coefficient. So it's 0.7. Square of that is 0.5, and that's a half. So you have the situation where the signal is attenuated by a factor of 2, going from one side to the other side. It's perfectly symmetric and reciprocal, and of course not lossless. And that's basically this describes this 3 dB attenuator. Okay, now this idea of reference planes, which is what I was wanting to elaborate a little bit more on here, is I think I'll make a new schematic. So let me call this one, in this attenuator 3 dB. Okay. I will make our favorite and most familiar LC oscillator. Okay. And I know that 1 nanohenry and 1 will give me something around 5 gigahertz. Let me just increase the Q factor a little bit by just changing the things by factors of 10. So reduce L by 0.10 and increase C by 10. Let's look at between 4 and 6. A new graph. It's a schematic 1. It's 1 angle. Let me just add the magnitude. Just should not AB. Okay, so we know this very familiar. The phase is on the left and the amplitude is on the right. So this gives you this plus 180 to minus 180 going through 0, and the magnitude is 1 as expected. Okay, and we also looked at this this effect of what happens when you put a transmission line, which is 50 ohms in between. Put that in again. Gigahertz, and I'll put a tuner on the electrical length. And now, of course, there is an additional phase wrapping, rolling of this thing. And as you increase the length of this line, of course, nothing is happening to the magnitude because this is a perfect 50 ohm transmission line without any loss. So we've already seen this. I'm just repeating it to remind you. So basically the resonance is sort of lost in this vertical changes, linear changes of phase with frequency, which is just this signal going back and forth. There's an additional phase which is being accumulated, and that phase is different for every frequency. So when you look at something as a function of frequency, you get more and more phase, and then that gives you this problem. I had shown you that in microwave office there is a type of measurement which allows you to get rid of that, which is called angle U, and then it just gives you, doesn't sort of wrap around after plus minus 180, but then plots it. Now you see this phase is going from 0 all the way to minus 120, 1200 degrees. That's the total phase shift. It's accumulated from this range to this range of frequencies. But the resonance is still not very clear, right? So in this kind of thing, you might not be able to see the resonance if the electrical length was very, very large. And this is what happens. And this can be done simply because this is just a mathematical change by adding this electrical length, which essentially cancels this out. It says that, okay, if there was an additional length of this type, I'll just add a phase as a function of frequency and cancel it out to get rid of this. But there is nothing happening in the magnitude as expected, okay? But suppose the, let's say this transmission line was not really 50 ohms, right? And something else was there, and I start tuning this thing now. And now you see more weird things start to happen, right? The magnitude here, of course, is still constant because everything is still lossless, right? The whole network is still lossless. This is just a transmission line with a different impedance, and this is a lossless LC resonator. So the magnitude is still not changing, but now you see this phase is developing all kinds of weird additional things. It doesn't even look like that there is only one resonance anymore, right? And why is that? Because now there is a reflection at this point and there is a reflection at this point. So this section of a transmission line is now a resonator. It's not a very high Q resonator because the impedance of this is not very different from 50 ohms, but that is now setting additional reflections. And this is a bad situation to have, right? This cannot be undone so easily, even if you do the calibration kind of situation. Now you have, so even if I did this angle U, this is how it looks like. And this is quite typical. And in fact, Joydeep and Supriyo, you guys have done these measurements. You get all these weird ripples and other things which show up in your broadband phase response. And these are all essentially due to reflections. Here, this is a simplified model where I've made the transmission line to be different. This, of course, doesn't happen. You never end up using accidentally a 100 ohm transmission line. What ends up happening is that this is actually still 50 ohms, but the connections of this cable to this resonator and this cable to the 50 ohm port could have some reflections here, like the transition I was just showing you from the book. And that can also make this entire section of the transmission line into a resonator. And then the response of that resonator is going to ride on top of the actual reflection coefficient you are interested in. Okay, so these are two different kinds of problems. One which is just a deterministic phase wrap. Even the other one is deterministic, but you will not usually know what's the properties of this thing to be able to undo this. Okay, it's not so easy. You could, if you had a model, then you can probably do this, but most cases you won't really know what's going on with this object. So, and if there is too much going on with this object, even the calibration procedure won't work very well. Okay, this we will see later on what kind of things can be calibrated out. Okay, so this was about just a section of transmission line and then mismatches, which gives rise to additional resonances. And these are all very common things which happen, not as exaggerated as what I showed you, but it happens in real setups and one needs to know how to deal with it. And particularly, this is a problem for cryogenic measurements because your instrument, which is sort of represented by the port here, is at room temperature, and your device, which is say your cavity, which you're trying to measure, is inside the fridge with a meter of cable in between them. And the calibration procedure, which I just briefly explained to you, requires replacing this device with known objects, so that you can say, okay, this is an open, this is a load, this is a short, or something else. And that, of course, is very challenging. How will I do this when this object is inside a fridge? The only real way, and in fact, people often do this, is to first connect some device here whose properties cool down, measure, warm it back up, change it, do it again, and then you do that. There are some tricks with certain devices you can play where, sometimes this thing is composed of some active device like a Josephson junction, and you can pass a current through it and turn it into a resistor. If you don't pass a current through it, then it's sort of an inductor. And in some cases, there are ways to even turn it into an open, and people do this. So you need some in situ way of, changing this into a known object so that you actually know what the reflection coefficient must be. And then you can do some calibration. There is another way where you can actually insert a switch between the end of this line and your device. So what happens is that now this is going to this point is inside your fridge. You can now connect this to a switch, which it's like a single pole multi-throw kind of thing. Okay, so then this will go to one standard, this will go to another standard, this will go to a third standard, and the fourth one will come to the device. So this is disconnected here. So then in the same measurement cool down, and you have to make sure that all of these lengths of the cable, everything is identical, so that you do the calibration properly. And there are switches like that available, we have in our lab as well. And some people use this to do in situ calibration in a cryogenic environment. Okay, so this is not directly connected to microwave engineering in that sense, but it's a practical way of doing that. Okay, so then you can take care of this. Okay. All right.
One question is how these switches work. Like they have some transmission line segment which moves around, or like
yes. Well, there are two types. There are the one which, for example, we have in our lab uses solenoid to move things. So it's actually a small coil which moves a piece of transmission line up and down so that it makes or breaks connection. Those are good or better in the sense that once that connection is made, then it's sort of looks like an ideal connection. There is no reflections and all. It can be minimized. But when they switch, it's a mechanical action. And it's kind of funny, but the amount of heat that is generated by two metals banging against each other at such low temperatures is actually significant. So you heat the fridge a little bit when you do that. So if you're doing one switch and then you're going to measure for hours, it's okay. But if you're going to do back and forth, then it can actually heat the fridge significantly. There are other ones which use semiconductor pin diode switches, where essentially by changing the diode's biasing condition, you can make it into a short or an open. So those are electronic pin diode switches. They have less ideal properties in terms of reflection and also insertion loss. Like it might not be a perfect connection. There'll be some attenuation in it, but they can be switched very, very fast. Like in nanoseconds, in tens of nanoseconds, you can go back and forth between an on and the off state. So that also has some advantages. So we have, I think, one pin diode switch, but that's actually for room temperature operation. Again, that's the problem with cryogenic things. Not all electronics actually work because the carriers just freeze out, and then the standard silicon electronics don't work. So some of these, but there are actually a lot of off-the-shelf components available here, which are just so that they still work at low temperatures. And often at lower temperatures, they work at very different bias points and all, but they do exist. We have these electromechanical
Okay.
ones in our lab actually installed. We actually use them to test multiple devices in the same measurement line. So that way they're quite
Okay,
handy.
okay.
Okay. So
Okay.
one last point I wanted to mention in this context of what kind of objects are okay and what's not. So if it's simple transmission line, it's fine. You can just cancel it out. But if you now had like to make it simple, let me get rid of this. And let me see if I can find that component. Yeah. So if I have an attenuator, so this is a 3 dB attenuator in a 50 ohm system. And this attenuation could represent the attenuation of the cable connecting your your network analyzer to your device. It's always often happens. Then what happens to the reflection coefficient? Okay, so let's go back to normal one. Suddenly now this starts to look different. Okay, now the first thing is the phase still looks fairly okay. You can spot the resonance, but the magnitude, so note the axis on the right side, it's now, earlier remember it was 1. Okay, so let me actually fix the scales here so that we can now see what's going on when the things changes. So this is good. This one I will go from 0 to 1. Okay. I'll put a tuner on this. Yeah. Minimum 0, maximum. Oops. So when the attenuator is 0, the magnitude response is as before. It's as if it's not there. The phase looks fine. Let me freeze this for reference. Now, as I increase the attenuation, you see that there's very little change in the phase, but the overall magnitude at, when I'm not zooming in, still looks flat, but the value has come down to something like half, right? Now again, remember that this is 0.5 in amplitude, not in power, because that's what we have plotted here. This magnitude doesn't refer to power. If we want to be, well, no, I think that will then scaling problem. So it doesn't mean that it's half power. Okay, it's actually 1/4 of the power, because 0.5 square is 0.25. How can we understand that? It's very simple. The power going this way is going to become half. Half of the power will be lost here. The power will be fully reflected because this is lossless. And then when it travels back again, it's going to experience another 3 dB loss. So it will become 1/2 of 1/2, which is 1/4. Okay, so that's why this is at 1/4. But you see that with just 3 dB attenuation here, in terms of knowing about the resonance, things have not really changed, right? I can still see the resonance fairly clearly. Looks nice, and okay, I'm getting much less power out. And this is something very important to also remember, that the moment you put a loss here, it experiences loss in both directions. So you get double the loss when you're doing a reflection measurement like this from one end. Okay, so it's much worse than you think it is. And this has consequences for signal to noise ratio, because you excited with some amount of power, 3 dB less is going on. Okay, so you will say, fine, I know this. So let me just increase the power I have put in by 3 dB. Okay, that will compensate the power reaching the device, but you will not compensate what happens to the power which is coming out in the other direction, right? You're always going to experience 3 dB loss there. So the incoming part can be compensated by putting more power, but the outgoing part cannot be compensated. And this again is a practical aspect that you will suffer signal to noise ratio issues if you have a setup like this where the reflection path contains losses. Okay, there are some configurations where this will not matter. I'll discuss that later on when we look at those kind of setups. But how far can this work, right? 3 dB is a small amount of loss, it's fine. But if I keep increasing this to larger and larger value, then this amount of signal coming back is extremely small, okay? Now, what is misleading, however, here is that this guy seems to be still completely the same, right? And this is because microwave office, is just a numerical calculation. But what's going to happen in reality is that the signal to noise ratio on this phase measurement is going to suffer dramatically. Even if you put a lot more power, unless you're able to put, compensate for both the incoming and outgoing power, then you will get back the reflection. You will not suffer from signal to noise ratio. But quite often in realistic devices, you cannot put too much power before this device starts to break. It could have some non-linearities. It could be some other, there could be even heating. In fact, in the, I guess Jay and Sujita, we had discussed that we can't put these losses at low temperatures because then it will dissipate too much and heat the fridge. So here it's kind of misleading because the phase response is unperturbed here. You don't see that things are going wrong, but with a 20 dB attenuator, you're going to get only 1% of the power which you send in back, and then that can cause an issue. And how do you even interpret this reflection coefficient? Because the reflection coefficient magnitude looks 0. So in fact, from the point of view of interpreting the reflection coefficient as an equivalent termination impedance, you will say, oh, this looks like a perfectly matched load because very little power is coming out. So you will not even think of this that there's actually a resonator there. It might just look like just a 50 ohm resistor, except for the fact that there's this phase response, which is going to be very difficult in practice to see because of the signal to noise ratio. However, what is more problematic in interpreting is this aspect that you really don't know. I mean, in this case, because it was a simple LC oscillator, you sort of knew that its reflection coefficient in magnitude is always unity. So any loss being experienced must be due to something in between and not in the device. But what if you are actually trying to measure the magnitude reflection coefficient of the object at this end? Then this kind of an attenuation like 20 dB basically completely masks the reflection here. And this is connected to the, in a different context, we discussed this yesterday, that when you have a large attenuator, it basically looks like 50 ohms on this side, and doesn't matter what is on the other side because the signal from that other side is barely going to make it back here. Okay. So lossy sections in between are very bad. They cannot be calibrated out because they will not kill the signal. They cannot recover the signal to noise ratio, right? A calculation can only scale the number, but it will scale both the signal and the noise. So signal to noise ratio will not be recovered, and you cannot measure the magnitude reflection coefficients carefully if you have a big attenuation in the middle. So it's very important to keep this in mind and make sure that you don't have losses when you're looking at reflection coefficients like this. Okay, so I think I want to stop there for today. I'll take some questions and then we will continue Some more, now we'll sort of look at more practical scenarios where you're doing these kind of reflection measurements and measuring scattering parameters and then trying to understand where what matters, and we will sort of build on some of these ideas we discussed today. Okay, any questions?
So this is with respect to the calibration that you were discussing. When
Yeah.
you are when you're not able to connect the device directly.
Yeah.
So I saw in the lab that Sumeru was characterizing some device, and what he did was he took the response of the wires without the device and then subtracted that sort of like background. Uh, so in which cases is this a reasonable thing to do, and when do you need to do the calibration with an
Right.
actual?
So that's a very good question. So what Jay is describing is the case where you are only interested in the transmission as a function of frequency for a device. And an example would be a filter, right? A filter has some transmission, and then it will change as a function of frequency. It could, if it's a low pass filter, it will be high, and then after some frequency it will start dropping. And if it's a high pass filter, it will be the opposite. It will be low first, and then it will increase and come to the. And in that case, you are mostly interested in knowing two things. One, what is the frequency when it starts to change, and two, when it is fully transmitting or fully stopping, what is that attenuation, right? So ideally a filter in its transmitting bands would have zero attenuation, but any real device will have some small amount of attenuation. And then when it is rejecting, you need to know how strongly it is rejecting. Is it 20 dB, is it 40 dB, is it 100 dB? Because that tells you how much protection you are getting. Now, if such a filter is connected to your network analyzer with cables, now that cable could have its own loss, right? They will have some loss, usually few dB per meter or something like that. So what Jay was describing is that what Sumeru must have done, he must have taken those two cables, connected them together, and measured the response of that, and use that as a reference. So either you just say that I will note that value, but usually it's a frequency dependent number, so you can't really do it by hand. So in the network analyzer, there's something called a memory trace. So you save that trace to memory, and then you disconnect the cables and put the device back, which for example could be a filter or an attenuator or even a splitter, for example. And then you can do something called data divided by memory. Okay, and that just takes out the reference and the frequency dependence as well off the cables. And it's a approximate way of doing, but a faster way of doing it without having to do a full calibration. This technique will not give you the reflection coefficients correctly. So a filter will have, it's a two-port network, so it will have S21 and S11, and it's symmetric, so the other two parameters are the same. So if you're only interested in S21, which is true for most filter characterizations, then this is a reasonable thing to do. But if you want the reflection coefficient, then the losses will prevent you from seeing that, just as we saw here, because from the point of view of port 1, the reflection coefficient looks close to 0. So you might be you might be tempted to say that, this has very good absorption. It's very well matched. But it's actually not matched at all, because on this side you have a perfect reflector, and this is what you are trying to measure. And this attenuator is completely masking that. Okay. So is that make sense?
Yeah, makes sense. And I guess in the case, of S11 and S22, it's probably, you don't need wires to connect it. That's why it didn't pose a problem.
In case of what?
So you said that for S11 and S22 or things like that, you can't really use this background data divided by memory.
Yeah.
And I guess he needed wires in the practical sense to connect two different ports to the VNA. Whereas for S11 and S22, you just need to connect one port and sort of match all the others to 50 ohm. So
yes, that's probably true. I don't know which example you saw, but it's true that you can now connect the filter or that device directly on the network analyzer and just put a 50 ohm port on the other one, and then you can get S11 and similarly S22. Yes. No, so, quite often it's for various reasons, sometimes just practical, sometimes laziness, that, the network analyzer already has this long cable connected, so I don't want to remove it and redo it here. So I'll just look at it at the other end. But yeah, there are various reasons for that. Sometimes those cables are part of a measurement setup, so you want to account for that, or sometimes you want to basically take that account, remove that attenuation of the cable to know what's going on in the fridge, for example. So yeah, so the bottom line is, if you're only interested in transmission as a function of frequency, then this is a reasonable thing for simple devices like attenuators, filters. But if we are, really want to know the full situation, the full scattering matrix, you can't get this. And even in that case, there will be small errors, because reflections can turn into transmissions if things are not matched up correctly. So a lot of this you will sort of see from experience as you measure these things.
Okay, yeah, got it.
Anybody else?
So in this case, AWR, so we are measuring the reflection using a single port.
Yeah.
But in experiment, we use 2 port to measure the reflection, let's say.
That's right.
So yeah, so how in this case it is measuring only from port 1? I mean,
I mean, even in experiments, when you do it at room temperature, you can measure a single port reflection coefficient. There's no problem with that. The reason for doing it effectively as a 2-port at low temperatures is because you don't want the signal path to be the same for going in and coming out. So this is going to be part of the next lecture. It's basically again related to the fact that the incoming line has a lot of attenuation deliberately put in to protect the device from the noise. Whereas the signal which is coming back, you want to capture as much of it. So if you use the same path, which is exactly the situation I have drawn here, you will basically not learn anything about the device, because the signal coming back will experience the same attenuation. And in a cryogenic environment, you need a minimum of 60 dB of attenuation to protect your device from the room temperature noise. So in that case, you will not see anything, because this attenuator will completely mask the signal. So what you do instead is that you put a device next to this thing, which is this circulator or a directional coupler, which allows you to separate the ingoing wave and the outgoing wave at the low temperature. And then the outcoming wave is sent through a different path, which has amplifiers instead of attenuators. And then you do that. So I will be discussing this in the next class in more detail. And we will again see what are the good practices there, how to do it, what are the problems when you do that. Okay. Last question? All right. So if not, we'll stop here. And I guess next class is tomorrow. Yeah, tomorrow at 5. Again, I might have to move it around a little bit, but I will update you in the morning. Okay. See you tomorrow.